Good day to everyone. So in the last video, we have discussed about the modified Euler's method, that is called the Huygens method, and how this Huygens method is used to numerically integrate the differential equation. So in this video, what we are going to do is we are going to see the other method, which is one of the famous method, which is called the Runge-Kutta method. So indeed, the Euler's method and the Huygens method, modified Euler's method, everything is actually a broad class of one-step approaches, which is also called the Runge-Kutta method. Now this formally derived the Runge-Kutta method. So the Runge-Kutta methods actually gaining accuracy of a Taylor series approach without requires the calculation of the higher derivative. So this Runge-Kutta method is having the various different variations of second order Runge-Kutta method, third order, fourth order, and fifth order, and it's actually having the infinite order. But if you write this Runge-Kutta method in the general form of y of I plus 1, which is equal to y of I plus some phi of the function of xi comma yi comma the time step h multiplied by the time step h. So this is the general form of the Runge-Kutta method. So where this phi is phi of xi, yi, comma h, it is actually called as the increment function. So the increment function, which can be interpreted as a representative slope over the particular interval of h. So this the increment function can be written in the general form of so the phi can be written as some a1 k1 plus a2 k2 plus a3 k3 plus and so on up to the n number n an of kn, in which the a1 a2 up to an is the constant and k is nothing but the slope, which can be written as the k1 k2 k are the slopes. So I can write this k1 is equal to some function of xi comma yi. So that is the slope of the corresponding differential equation which we are using. Similarly, the k2 can be written as the f of some xi plus p1 times of h comma yi plus q11 times of k1h. Similarly, the k3 can be written as k3, which is equal to the function of xi plus p2 of h yi plus q21 times of k1h plus q times q of 2 to k2 of h. So similarly, I can write the nth form of the kn, which is equal to f is f of xi plus p of n minus 1 times of k comma yi plus q times of n minus 1 comma 1 times of k1h plus q of n minus 1 comma 2 k2 of h plus similarly I can go further up to the nth function k to q of n minus 1 comma n minus 1 k times of n minus 1 times of h. So this is I can write the slopes k1, k2, k3 up to n. Here the p and the q are the constants. So here we can note that each and every case the sequence having some relationship, that is the k1 is actually appears in the k2th function, and similarly k2 is actually appearing in the k3. Similarly, the k3 will appear in the k4 and so on. So the the n minus 1 will actually appear in the nth function of the k. Because each k is a function evaluation, this recurrence makes the Runge-Kutta method efficient for computer calculations. So as I already told you that there are various types of Runge-Kutta methods can be derived by employing different numbers of terms in the increment function as specified by the n. So for the first order Runge-Kutta method, the n value will be 1. Suppose if you put n is equal to 1 in this equation, which is nothing but the Euler's method. So if you choose the n with a particular value, the corresponding values of A, P and Q are evaluated by just setting the corresponding equation, the phi equation in terms of the Taylor series expansion. For an illustration, I will explain how this for the second order RungeKutta method is actually derived from this expression for n is equal to 2. So if I choose n is equal to 2 in this equation, then I can write this phi is equal to a1 k1 a1 into k1 plus a2 into k2, which can be substituted into this equation, so that I can write the second order RungeKutta equation as so I can write the y of I plus 1, which is equal to y of I plus the the function phi can be written as a1 k1 plus a2 k2 multiplied by the time step h. So this is the second order RungeKutta method, where this k1 and k2 can be written as k1, which is equal to function of xi comma yi. Similarly, the k2 can be written as function of xi plus p1 into h comma yi plus q times of 1 k1 times of h. So which can be derived from this the which value which we have found from the k1 and k2 values. So these are all the two values. So once if you try to derive the second order RungeKutta method, you can easily calculate the values of the a and b, sorry, a1 and a2. Similarly, the p and q, which will be like the a1 is a1 plus a2 will be equal to 1. Similarly, the a2 p1, which is equal to 1 by 2. Similarly, a2 q11, which can be also written as 1 by 2. So we can just using this the equations, I can write the second order RungeKutta method. So here you can see that we have a 3 equations, but we have a 4 unknown values. Suppose if you want to find out the values, we must assume the value of the one of the unknowns to determine the other 3 of them. Suppose that if you specify the value of a2, then these equations can be solved simultaneously for a1, which is equal to 1 minus a2, and similarly p1, which is equal to q11, which is equal to 1 divided by 2 times of a2. So we can solve this only if you know the value of the a2. So because we can choose the infinite number of values for a2, there are infinite number of second order RK methods also available, or can be generated by just varying the or choosing the value of this a2. So the every version would yield exactly to the same results in the solution of the corresponding ordinary differential equation. For example, if I choose the a2 value is 1 by 2, then if I substitute this value in this equation, then I will get the value of a1, which is equal to 1 by 2, and similarly a2, which is equal to 1 by 2. Similarly, the p1 and q11 is also having the values of p1, which is equal to q11, which is also having the values of 1 by 2. And if you substitute these values into this equation, then I can get y of I plus 1, which is equal to y of I plus 1 by 2 times of k1 plus 1 by 2 times of k2 multiplied by the times h, so that I can write the k1, which is equal to a function of xi comma yi. Similarly, the k2, which is equal to f of xi plus p1 is half, so that I can write as a sorry, the p1 and p2, the p1 and q1 having the values of 1, so that I can write this k2 is equal to f of xi plus h comma yi plus k1 into h. So which is nothing but this equation is nothing but the modified Euler's equation, that is the Xournal's method, which we have seen in the previous class, where the k1 and k2 are the slopes, which can be defined by this equation. So if you choose this a2 is equal to half, this second order RungeKutta method can be converted into the Xournal's method. Similarly, if you choose the a2 is equal to 1, then you will get the different approximation method. So if I want to precisely tell that a2 is equal to 1, then the corresponding the equation will be equal to the midpoint method. And similarly, if you took the a2 is equal to 2 by 3, then the method which we have derived is the Ralston method. So therefore, based on the values of the a2 which we are assuming, we can come up with a different method from this second order method. Okay. So so here we have chosen the n is equal to 2, so that we can come up with the second order Runge-Kutta method. Suppose if I choose the n is equal to 3, then the derived equation is actually called the third order Runge-Kutta method. So for n equal to 3, it is actually the third order RK method, the Runge-Kutta method. So which the final equation is actually look like y of I plus 1, which is equal to y of I plus 1 by 6 times of k1 plus 4 k2 plus k3 into h, where this k1, k2, k3 are the three different slopes. So I can write k1, which is equal to some function of xi comma yi, the k2, which is equal to the function of xi plus half h comma yi plus 1 by 2 times of k1 into h. Similarly, the k3, which is equal to function of xi plus h comma yi minus k1 into h plus 2 k2 times of h. So this is the slope values of k1, k2, k3. That means suppose if you are trying to if you to put the x is x and y, and x is actually varying with respect to xi, I plus h. Suppose if you are finding out the solution of using the initial condition, you are actually in the Xournal's method. Actually, you are using this point as a starting point. You can just predict the method, and then you can again finding the slope at this point. Then you can take the average of these two slopes. Then you get the Xournal's method. However, in the third order Runge-Kutta method, what you are going to do is you are going to find out three slopes. So the first one is the k1, and this is the k2. So this is k2, and similarly you can again find out the another slope intermediately, k3. So that this actually may be a k3, and you can find out the different slope 3 times of you can find the slopes, and you can take the average of these slopes, which will give you this the third order Runge-Kutta method. So in a similar way, suppose if you took n is equal to 4, then you will come up with the solution of the fourth order Runge-Kutta method. Fourth order Runge-Kutta method, which is one of the famous RK methods, which is actually still using for to solve the differential equation. So this fourth order Runge-Kutta method is a commonly used method to solve the differential equation, which is called the classical Runge-Kutta method. So y of I, the equation is actually y of I plus 1, which is equal to y of I plus 1 by 6 times of k1 plus 2 k2 plus 2 k3 plus k4 times of h. So this is the value in which we are actually taking the slope 4 times k1, k2, k3, k4, which is having the values of k1, which is equal to the function of xi comma yi. Similarly, the k2, which is equal to the function of xi plus 1 by 2 times of h comma yi plus 1 by 2 times of k1h. The k3, which is equal to the function of xi plus 1 by 2 times of h comma yi plus 1 by 2 times of k2h, and similarly k4, which is equal to the function of xi plus h comma yi plus k3 times of h. As I already told you that each and every k, the previous value of k is actually applicable and applied, which is presented in the next slope. For example, you can see this in the k2th slope, you can find out the k1 will be available. Similarly, the k3th slope, you can find out the k2. Similarly, then the k4, you can find the slope k3. So the graphical representation of this slope is actually given here, where you can actually using the initial value of xi, you can interpolate the xi plus 1 using the predictor method using the first the first slope using the k1, and similar for the k2 and k3 is actually finding the slopes in between the xi and xi plus 1. That means in the terms of h by 2. So in this in between this xi and xi plus 1, you are actually having the another slopes, which is actually k2 and k3, and using this k1, k2, k3, similarly the k4 is actually also predicted using this form, so that if you take the average of this all the four slopes k1, k2, k3 and k4, then you will get the approximated, that means almost close to the exact solution. So based on the time step which we have chosen. So now using this the fourth order Runge-Kutta method, this formula, we can solve the differential equation. So I will illustrate one of the examples to solve the differential equation using this the fourth order Runge-Kutta method. So the example sum is, how to solve this initial value problem dx by dt, which is equal to minus 3x plus 2y, where the initial condition of x at t equal to 0 is 0. Similarly, dy by dt is equal to 3x minus 4y, where the initial condition of the y is given as 0.5. So the time step is given as h is equal to 0.2. So you have to find out the solution of in the interval of 0 to 0.4 using the fourth order Runge-Kutta method. So you can see this is a system of equation where you have a coupled system of equations. So you have to independently derive the x and y using this Runge-Kutta method. For example, you have to calculate the slopes for the dx by dt, and you have to calculate this k1, k2, k3, k4. Similarly, you have to calculate the same slopes for the dy by dt also, and then you have to find out the average. The f of xy for the f of xi yi for the x variable is minus 3x plus 2y. Similarly, the f of xi yi for the y variable is 3x minus 4y. So these are the two functions which you have to find out using these two functions. You have to independently calculate the solutions of the x and y using this fourth order Runge-Kutta method. Okay, so this is the equation which you have to remember. So based on this equation, first you have to calculate the slopes, and then you can find out this average using this equation. Okay, so first we should start with this I equal to 0, the iteration I equal to 0. So the solution for I equal to 0, we have t equal to 0. That means the t0, the initial value t0 equal to 0. Similarly, the x of 0, the initial condition of x of 0, which is equal to 0. Similarly, the y of 0, which is equal to 0.5. So these are all the values we have for the initial condition. So first we have to find out what is the slope. That means k1. So since we are having the two different variables x and y, we can indicate the x k11 and k12, k13, k14 for the x variable. Similarly, k21, k22, 23, 24 can be taken as a y variable. Okay. Okay. First, we are going to find out what is the k11. So k11, which is equal to h into the function of t0, x0, comma y0. This function is actually given as, since we already know this the value of h. So here you can see this instead of multiplying this entire slope divided by h, what I am going to do is every time I am going to multiply going to use the the function of h in the calculate the k1, k2, k3, k4, and then I can use it in the average equation without this without this h. Okay. So I am going to first find out the slope for this f of t x0, y0. This multiplied by the value of h. H is given as 0.2. So 0.2 times of this the function is given as minus 3x plus 2y, so that I can just write the equation minus 3 times of x0 plus 2 times of y0. So we know this x0 and y0 values. The x0 value is 0 and y0 value is 0.5. I can substitute these values here. I can write 0.2 times of, this will be 0 plus 2 times of 0.5, which is equal to 0.2. Okay, so my k11, the slope of the k11 will be equal to 0.2. Similarly, I can find out the slope of this y. That means I can take it as a k21. So k21, which is equal to h times of function 2. Suppose if let us take this as the function 1 and this is function 2 of t0 comma x0 comma y0, which is equal to h 0.2. The function of the y is given as 3x minus 4y, so that I can write 3 times of x0 minus 4 times of y0. Now I already know these values for x0, y0. I can directly substitute the values 0.2 times of 0 minus 4 times of 0.5, which is equal to 0.4. Therefore, my slope of k21 is given as 0.4. So similarly, I can find out the next slope k12 for the x as well as k22 for the y. So the k12, which is equal to h into f1 of t0 plus h divided by 2 x0 plus k half times of k11 plus comma y0 plus k21 divided by 2. So this is my the k12, that means that this slope xi plus half into h and yi plus half into k1 into h. Here we have a x as well as y, both the x as well as y. So I can write this as the t is actually very good to h by 2 and y is actually x and y is actually having the slope of k11 and k21 divided by 2. Okay, so I can write this as a half into k21. Okay, now I know these values of k1, k11 and k21, then I can directly substitute this in this equation, so that it is equal to 0.2, the function 1 of the t0 plus h by 2, t0 which is equal to 0, h we already know that is 0.2 divided by 2, I will get 0.1, comma, and x0 is 0 plus half into k11, k11 is actually 0.2 divided by 2 will give it the 0.1, comma. Similarly, the k21 is actually having the value of 0.4 divided, the y0 is 0.5, so 0.5, sorry, this is actually having the minus value, so that 0.5 minus this 0.4 divided by 2, I will get 0.2. Okay, so I hope you understand how this values came from. The t0 is 0 and plus h is equal to 0.2, so 0.2 divided by 2 you will get 0.1. Similarly, x0 is 0 and k11 value which we have calculated here 0.2 divided by 2, which will get the 0.1. Similarly, y0 value which we have 0, the initial value is 0, and the half the k21 slope, the k21 slope we have calculated as minus 0.4. Sorry, the y0 is actually 0.5. So the 0.5 minus of 0.4 divided by 2, you will get the 0.2. So just calculating this value, I can write 0.2 times of f1, 0.1 comma 0.1 comma 0.3. So these are all the values of t0, x and y. So I can just substitute it into the same equation, the same slope. I mean that this equation x and y, I can get the answer as is equal to 0.2 times of minus 3 times of 0.1 plus 2 times of 0.3. Okay, suppose if you do the arithmetic operation, you will get the value of 0.06. That is the slope of k12. Similarly, I can calculate the k22, which is equal to h into f2 times of t0 plus h divided by 2, x0 plus half times of k11 comma y0 plus half times of k21, which is equal to 0.2 f2 times of, again I can substitute the values of t0, h, x0, k11, k12, y0, everything in this equation. You will get the numbers 0.1, 0.1, 0.3 as usual. Now again the same values will be substituted into the y equation, that is the 3x minus y. So I can get 0.2 times of 3 times of 0.1 minus 4 into 0.3. That means this is the 0 t value, this is x value, this is y value. So I can get the value of minus 0.18. That is my k22 value. Okay. Similarly, I can calculate the next slope k of 1 3, which is equal to h into the function 1 of t0 plus h divided by 2 comma x0 plus half times of k12 comma y0 plus half the times of k22. Okay. Now I can again substitute the previous values which we have calculated k12 and k22 in this equation, and then we can find out the k13 as well as the k23. Okay. So the 0.2 into f1 of 0.1 comma 0.03 comma 0.5 minus 0.09, you will get the values as 0.2 times of f1, 0.1, 0.03 comma 0.41. Okay. Now we can substitute this x and y values in the y equation. Like the x equation, I can get 0.2 into minus 3 times of 0.03 plus 2 times of 0.41, which is equal to, so we could get the final equation as final value is 0.146. That is my k13 value, and the k23 I can calculate k23, which is equal to again h times of the function of h2 f2 t0 plus h divided by 2 x0 plus half k12 comma y0 plus half k22. Again I can substitute the same values here. f2 of 0.1, 0.03, 0.41 into the flow the y equation 0.2 times of 3 times of 0.03 minus 4 times of 0.41, which will give you the final value as minus 0.31. So that is my value of the slope is actually k23 is equal to 0 minus 0.31. Similarly, the final slope k14 can be calculated as h into function f1 t0 plus h comma x0 plus k13 y0 plus k23. Okay, that is the formula. So I can write 0.2 function 1 of 0.2 comma 0.146 comma y0 value is 0.5 minus 0.31 value, that is the k33 value, which is equal to 0.2 times of minus 3 into 0.146 plus 2 times of 0.19. So just to the final value of this will give 0.19. So the k14, the slope the k14 of the slope is minus 0.0116. That is the k14 slope. Similarly, the k24 slope, this is equal to h into function of 2 t0 plus h comma x0 plus k13 comma y0 plus k23, 0.2 times of function f2, again the same value 0.2 comma 0.146 comma 0.19. I can substitute the values in the second equation 0.2, 3 times of 0.146 minus 4 times of 0.19, which will give you the answer as minus 0.0664. So that is the k24 slope. Okay. Now I have already calculated all the slopes, so that I can find out the final equation, the average. The average is actually nothing but the y of I plus 1 is equal to y of I plus 1 by 6 times of k1 plus 2k2 plus 2k3 plus k4. Okay. Because I have already used this sketch in by calculating the slopes, so that I can write the final slope of x of 0.2. That means that we have already know the value of x is 0 at the time step of 0.2. We have calculating with this x of x I plus h. We are actually calculating this value, that is actually 0.2, which I taken as x1. The series x of I plus 1, so I can take it as a y of I plus 1. I can take it as a x of 1, which is equal to x of 0 plus 1 by 6 times of k11 plus 2k12 plus 2k13 plus k14. Okay. Now I can write x of 0 is 0 plus 1 by 6. Though I know all the slope values k11, k12, k13, k14, I can just substitute the value 0.2 plus 0.12 plus 0.292 minus 0.0116. Okay, so the final value is, that means that the x1 value is 0.1001. So this is the first iteration x1 value. Similarly, I can find out the y of 0.2, which is equal to, I can write as y1, which is equal to y0 plus 1 by 6 times of k21 plus 2 times of k22 plus 2 times of k23 plus k24. So I know all these values now, right? So I can just substitute the values here. Y0 value is 0.5 plus 1 by 6 times of minus 0.4 minus 0.36 minus 0.62 minus 0.0664. So the final value is, there is the value of y1, which is equal to 0.2593. So this is the value of x and x1 and y1 for the time step of h is equal to 0.2. Okay. Similarly, I can do the next iteration for I is equal to 1. We have t1 which is equal to 0.2 now, and x1 is equal to 0.1001 and x2 which is equal to 0.2593. Now taking this as a initial conditions, you are actually calculating the x of I plus 2h, you are going to calculate. Okay. Similarly, I can calculate the slopes again, k11 which is equal to h into f1 of t1 comma x1 comma y1, which is nothing but the 0.2 times of t1 value is now 0.2, or I can directly substitute in the equation. I can get minus 3 times of x1 plus 2 times of y1. Now I know these values here, so I can write 0.2 times of minus 3 times of x1 value is 0.1001 plus 2 times of y1 value is given as 0.2593. Okay. Now I can easily calculate the values of k11 now, which is actually having the values of 0.0437. So that is my k1 value. Similarly, I can calculate the k12 which is nothing but the h into f2 times of t1 comma x1 comma y1, which is equal to 0.2 times of 3 times of x1 minus 4 y1. Again I can substitute the values of 3 into 0.1001 minus 4 times of 0.2593, which will give the value of minus 0.1474. Okay. So similarly, I can calculate the k12, which is equal to h into the function f1 of t1 plus h divided by 2 x1 plus half times of k11 and y1 which is y1 plus half times of k21. Sorry, here this is actually a k of 21 and this is k12. So that's why I can just substitute this value here. So I can substitute the values 0.2, f1 of 0.3. Suppose if you substitute the values of t1, x1, k11 and y1, k21 and just doing the calculate the final values, which will be equal to 0.3 comma 0.1220 comma 0.1856. So these are all the t, x and y values, so that I can just substitute these values into the corresponding slope, that means the differential equation. So the 0.2 times of minus 3 times of 0.1220 plus 2 times of 0.1856, which will be equal to 0.0010. So that is the value of slope k12, and k13 will be equal to again h of f2 of t1 plus h divided by 2 x1 plus half k11 and y1 plus half of k21. Now 0.2, the function f2, again the same values. If you substitute these values, you will get minus 3 into 0. This is actually k22, which is equal to this, so that I can substitute the values of f2 as 0.3, values 0.3, 0.1220, 0.1856, so that the final value will be equal to 0.2. The slope value is 3 times of 0.1220 minus 4 times of 0.1856, that will be equal to minus 0.0753. That is the slope of the k22. Similarly, I can calculate the k13, 23, 14, 24. So the values you can just do it as a homework. So the value of k13, which is equal to h into f2 t1 plus h divided by 2 x1 plus half k11 comma y1 plus half of k21. This is 1 2 and this is 2 2. So if you substitute these values, we get if you substitute the values of k12, k22 in this value, the final value of k13 will be equal to 0.0283. Similarly, k of 23, which is equal to minus 0.1170, and k of 14, which is equal to minus 0.0201, and k of 24, which is equal to minus 0.0368. So now we have calculated all those value slopes. I can calculate the point at x is equal to 0.4. That means x of xi plus 2 times of h. So I can get x of 0.24, which is equal to x of 2, that is x of 1 plus 1 by 6 times of k11 plus 2 times of k12 plus 2 times of k13 plus k times of 14. So I can substitute the values k1, whereas x1 value is 0.1001 plus 1 by 6 times of the values of this k1, k2, k3 and everything. I can substitute the final value, which is equal to 0.1138. That is the value of x2. Similarly, I can calculate the y of 0.4, which is equal to y2 is equal to y1 plus half into k21 plus 2 times of k22 plus 2 times of k23 plus k24, which will be equal to the final value of y1 is 0.2593 plus 1 by 6 times of these slope values. So the final value y2, which is equal to 0.1645. Okay. So this is the values of x2 and y2 at the point of x is equal to 0.4. That is what we have to calculate. That means the values which we have to calculate is in the range of 0 to 0.4. So we have calculated the initial value is given as 0, and the 0.2 we have calculated the solution, as similarly the 0.4 we have calculated the solution for using the fourth order Runge-Kutta method. So this is how you can just completely iterate the each and every point, each and every iteration you can calculate this x and y values, then you can plot it as a solution. Okay. So instead of manually doing this, you can also write the programs using this the equation, just writing this, just converting this into the numerical algorithm and doing this program, then you can solve any differential equation, whether it's a simple equation or a complicated solution, or a complicated equation, linear or non-linear equations. You can solve it just converting this into the algorithm, the computer algorithm, which I will see in the next class. Okay. So if you have any doubts in this the Runge-Kutta methods, then we can discuss it in the online class. So this the fourth order Runge-Kutta method is one of the important, predominantly used method to solve the differential equations, the ordinary differential equations with initial value problems, so that you can use this to find the solution of any differential equation. Okay. Thank you.